Yes. Okay. So last time, basically, we talked a lot about this basically energy equation, how we actually apply it. It turned out that energy equation the conservation of energy equation basically turns out that it's related to, we obtained an equation basically whether um, stagnation enthalpy will change or not. That was basically the bottom line of the story. And we said, we actually, if you remember, gave some examples like along a streamline. We talked about, let's say, 4 different cases. So this is what we already discussed, but it will be important. So I will quickly revise this again. Non-adiabatic flow, adiabatic flow. So adiabatic flow meaning there is no heat flux. Non-adiabatic, there is a heat flux. So these lines are actually streamlines. So if we do have an initial condition like a initial enthalpy level H1 and the stagnation enthalpy level, then these may or may not change depending on whether we have adiabatic flow or not. If we have a non-adiabatic flow, the most important thing is that stagnation enthalpy will change. So it's not going to be equal to H01. We have discussed relevant equations last week. For the adiabatic case, though, if there is no heat addition, external heat addition to the flow, to the fluid particles as they're moving along streamlines, yes, then the stagnation enthalpy, and so therefore, for a calorically perfect gas, stagnation temperature must remain constant. It should not
Hocam,
change. Evet.
sorry to interrupt, but there is some problem with the video. I think if you turn off your camera, the network load will be less and the screen share will be better.
Okay.
Herhangi bir sıkıntı yok bence. Ben de normal şu an görüntünüz.
Bende de normal hocam gayet.
Bende de hocam.
Normal olmayan kimdi biraz önce? Kim
Ben.
söyleyeyim?
Ufuk.
Sen kimsin sen? İsmini göremiyorum.
Ufuk Ercan.
Ha, Ufuk, sana şey mi, whiteboard mu kötü geliyor?
Hem siz hem whiteboard böyle yazıyorsunuz, geriden geliyor. Yazdığınız şey sonra bir anda bir satır olarak falan. Çok mühim değil ama hani.
Tamam, bir de ne bileyim bir 5 dakika bir videoyu kapayarak deneyelim bakalım nasıl olacak. Okay, so first let me minimize this. Okay, I turned off the video. Let's see how it works out.
John, can I ask you a question?
Yes, please.
Can we make comments about the speeds and velocities in both situations? Is it possible?
Right, we will eventually do that, because the thing is, we will start talking about shock waves. So therefore we will talk about not velocities, but actually Mach numbers. So this fundamental discussion will be relevant to that. Okay. It will be coming. So let me write this down. But last week at the final minutes, we also said, okay, why don't we go one further step, meaning that, for example, if it's adiabatic, and what if it's also reversible? So we considered also flow for an isentropic case, so and a non-isentropic case. So for the isentropic case, so not only heat flux is zero, it's also reversible, meaning we ignore all the losses. So in this case, not only total temperature does not change. For the isentropic case, total pressure also does not change. Okay, and total pressure, if it's changing, the loss is basically due to, in fluid mechanics or in aerodynamics, due to viscous losses, due to boundary layers, and the details of which we're going to learn this semester. but those basically very fundamentally fundamental physics sense friction related effects, if they are if we are ignoring them, then nothing can change stagnation pressure. So there is no heat addition, and while the fluid particle is moving, there is no external work done on the fluid particle. It's just moving along. We don't have a propeller or anything like that, or we don't have a turbine or anything like that. And also everything is reversible. So basically, I can write in aerodynamics sense, no viscous losses. So under these conditions, isentropic flow, all these remain constant. Not the case for non-isentropic flow. For non-isentropic flow, it could be adiabatic, but so there could be no heat addition. But if it's irreversible, then the most important result is that P0, so if this is 1 and 2, P02 will be less than P01. You will lose some stagnation pressure. This is quite important in designing aerospace systems, including aircraft, including aircraft engines, including aircraft, including rockets, rocket nozzles. We will see all of these. So, in this sense, now we start. These are fundamentals, and these are all related to the energy conservation equation that we have started discussing last week. But now we will start talking about more, some of the flow physics that we encounter in high-speed flow, okay? And when we are when we have to design, high Mach number, especially supersonic flying systems, this could be a fighter aircraft, this could be, first of all, I must say that most of these applications will be some kind of military applications for supersonic flight. In terms of civilian applications, there was one civilian supersonic passenger aircraft, Concorde, what it was decommissioned, as you know. There are new efforts to come up with a new supersonic airliner. And also another civil application is, for example, companies like SpaceX, for example, trying to put spacecraft, satellites and other things into orbit. So of course they have to go through supersonic flight physics. So when things start flying fast, high Mach number flows higher than the speed of sound, we encounter certain physical properties of the flow which we do not have in subsonic flow. And one of the basic most fundamental ones are what we call shock waves. And we have actually, I have shown you, if you watch again our very first class video, I have shown you some videos of certain aircraft, flying or breaking what they call in daily language, breaking the sound barrier. So basically, in aerodynamics language, it's basically flying supersonically, Mach numbers greater than 1. So in that case, these flow structures occur in the flow, and we need to know their physics, and we need to know mathematically how to analyze flow properties if we have shock waves. So the general topic could be, maybe I can write general aspects of supersonic flow. We will first start with that. And when I say general aspects of supersonic flow, we will cover many things. We will cover flows related to what, or let me put it this way, what we call external flows. So flows happening around aircraft, for example, around your wings, around your fuselage. So happening external to the aircraft. Also, we do have internal flows that are related to internal supersonic flows. So these are related to, for example, rocket engine design, rocket engine nozzle design. So if you take a look at the rocket engines used by, you know, Russian aircraft, American rockets, whether SpaceX or NASA or European built or Japanese built rocket engines, they are all designed, I mean, they have special shapes, their nozzles, for example, they are all designed to handle supersonic flows occurring inside them. So we call this internal flow, internal aspects. The most important characteristic or difference that we observe, difference in supersonic flow compared to subsonic flow, is the existence of what we call shock waves. Okay, shock waves. So we do not have these in subsonic flow. In high subsonic flow, for example, you could be flying, let me give this as a side information, you could be flying at, I don't know, Mach 0.8, for example, high subsonic, but locally on the top of your wing, the flow could accelerate further. I mean, your flight speed could be Mach 0.8, but the flow could accelerate further and could become locally supersonic. That also generates local shock waves over the wing. So when I say shock waves occurring in supersonic freeze stream, it's you could be, there are two options. You could you could be flying in a total supersonic regime, or locally your the flow field around your body could be supersonic. So what is a shock wave? First of all, a shock wave is basically an extremely thin region in space. So let's designate this this region as a shock wave. Extremely thin region in space, and when I say extremely thin, it's probably in the order of 10 to the minus 5 centimeters or so. So the flow incoming, there could be a flow incoming towards your shock wave with some Mach number, let's say M1. So the streamline could be coming like that. And then after the shock wave, depending on what generates this shock wave, what kind of solid body generating this shock wave, the streamlines could change direction. So the flow direction could change and the Mach number will change. So the conditions before the shock wave is, let's call them 1. After the shock wave, let's call them 2. So M2 will not be equal to M1 after this shock wave. It's a very thin region and very, very viscous region in the flow. And the thing is, basically what's happening is, as if you're a fluid particle moving at, you know, upstream of this shock wave, as soon as you hit this shock wave, it's like as if you are hitting basically a wall. Okay, you experience sudden change, almost instantaneous change in all of the flow properties, not only Mach numbers, of course, in velocity, in temperature, in pressure, in density. Everything will instantaneously change to different levels. Okay, and of course, not only that, related flow properties such as stagnation values, P01, for example, P02, it will change. Okay, except for two important parameters that will remain constant across the shock wave, and one of them is the stagnation temperature. Stagnation temperature will not change across the shock wave because a shock wave is basically an adiabatic process. It's just, I mean, we do not have basically any heat addition occurring across a shock wave. There's no external heating applied to the fluid particles. So therefore, it is an adiabatic process. Is it a reversible process? No, it is highly irreversible. irreversible. So it is not an isentropic process. It is adiabatic, but it's not reversible, meaning that so therefore the stagnation temperatures will be the same because there is no external heat addition, but stagnation pressures will be different. Okay, so it's similar to what we were discussing about this energy equation in the beginning of today's class. So
Can I ask a question?
yes, please go ahead.
Can we say that the stagnation enthalpy is equal to stagnation temperatures?
Yes, we can say that. Since for a calorically perfect gas, and assuming C and Cp could change a little bit, but not drastically, it doesn't change a lot. So we can also say stagnation enthalpies also remain constant as well. Okay.
Thank you.
So this, when a shock wave, I mean, I said these parameters will change, these parameters will remain constant, but we did not talk about how they are going to change. For example, whether M2 will be larger or smaller, or T2 will be larger or smaller. We haven't talked about it, but before talking about it, I just want to say, if the shock wave it actually looks like in the sketch, meaning that it is sitting at a certain angle, let's say, at a certain angle to the flow direction that is incoming. By the way, this is like, you must understand, this is like a straight arrow. It is sitting at an angle. That type of shock waves are called oblique shock waves. Okay, so this is basically, in the sketch, is what we call an oblique shock wave. There is a special version of this where in this sketch where beta is 0. So if the shock wave is standing like this in the flow at 90 degrees to the incoming flow direction, let's say this is M1, so this is M2, let's say, this is known as a normal shock wave. We call it a normal shock wave because it's basically standing at 90 degrees to the incoming flow. In reality, we will first discuss properties of normal shock waves, and then we will further move on to to oblique shock waves, because it requires a little bit more different handling of the topic. So in terms of this relations between incoming and outgoing variables, when and keeping it general at this instant for keeping it an oblique shock wave, in this case, Mach number 2, the flow will slow down. Mach number 2 will be less than Mach number 1. Mach number 1. What else? V2 will be less than, V is velocity, V2 will be less than V1. The static pressure will be larger than P1, so that you will experience, or the fluid particle will experience, a sudden increase in static pressure. Static temperature will also rise instantaneously to a higher level. Since it's not, also, by the way, I forgot to mention entropy, for example. Since it's not a reversible process, S2 will be larger than S1. What else? Because of the irreversibilities and the fact that the shock wave, this very thin layer, is actually a very viscous layer. All the viscous effects are basically contained within this very thin shock wave layer and creating irreversibility. P02 will be less than P01. Okay, and temperature enthalpy will, the stagnation temperature, stagnation enthalpy will remain constant. What else? Yes.
Could you repeat your sentence about stagnation pressure?
Stagnation pressure at the exit will be less than the stagnation pressure at the inlet because of the very high viscous losses occurring inside the shock wave. Okay, it's a very thin region, but very, very viscous region. So because of that, that introduces irreversibility to the flow. Okay, you lose, the flow loses some of its stagnation pressure.
Teşekkür hocam. Bir de başka bir soru sorabilir miyim?
Yes.
We are talking about changes in these properties in the whiteboard, and we have two types of shock waves. One is oblique and one is normal. Which one affects most these properties? Can we talk about that?
Both of them. We will see more details. Okay, we will see more details. The thing is, this list that I made here is valid both for normal shock waves and oblique shock waves. Okay, but with one difference, and that difference is related to the Mach number at the exit. If you have a normal shock wave, regardless of the, and by the way, of course, M1 is always greater than 1, don't forget, otherwise we would not have a shock wave, whether it's a local M1 on your wing or whether it's actually you're flying supersonically, it's your flight M1, it's always must be supersonic, otherwise you would not have a shock wave. So well, if it's greater than 1, but how high is it? Is it 1.1 or is it 8, right? Regardless of the fact that how high M1 is, for a normal shock wave, M2 will always be subsonic. Always. There is no exception to that, okay? If you have a normal shock wave, M2 will be always subsonic. So, but this is not the case for oblique shock waves. That for oblique shock waves, M2 in most of the cases can be still supersonic. So it's just a reduction in M2. So the flow will experience deceleration. It will slow down, reduce speed, but it could still be at a slightly lower supersonic value. We will see the importance of this when, in terms of especially when we start discussing how these oblique shock waves are generated and what we need to be careful about. To repeat again, that's not the case for normal shock waves. It will always be subsonic after the shock wave. Other properties like pressures, temperatures, I mean, all the other discussion that we made is exactly the same both for oblique and normal shock waves, meaning that stagnation enthalpy remaining constant, stagnation temperature remaining constant, stagnation pressure decreasing, and other properties here listed like pressure, static pressures increasing, temperatures increasing. These are all valid both for normal and oblique shock waves. So good. So therefore, one note I could make is that for a normal shock wave, generally depending on the Mach number in front of it, depending on the level of M1, it could be if M1 is, let's say, low supersonic, so let's say 1.1. Compared to, let's say, another case, M1 hypersonic, let's say 6. In that case, of course, whether it's coming with a 1.1 or whether it's incoming with 6 makes a difference in terms of how much pressure rise that you're going to have, how much temperature rise that you're going to have. It makes a difference. And in fact, in this class, what we're going to learn is to how to calculate the properties after the shock wave, given the properties at the inlet, and these could be mostly related to your flight conditions, meaning flight Mach number and flight altitude. Given those flight conditions, and if your aircraft has a shock wave on it, on its wings, on its nose, how do we calculate the values after the shock wave? That's what we're going to learn in this class. And depending on how high M1 is, and also from the equations, we will see that it makes a big difference on the properties downstream of the shock wave. So after, behind the shock wave, I must say. Okay. Okay, let's continue. And let me check my notes if I missed anything. Okay, good. So we will first, okay, let me make one more point. It's not in the notes, but let me explain also. The thing is, you know, these kinds of shock waves are observed in many flight systems. So if you have like a supersonic flying missile, let's say, if this is the nose of the missile, if it's flying at a certain supersonic speed, you will end up with an oblique shock wave attached to its nose. It will look something like that. If generally, if it has a blunt, what we call a blunt nose, so it will look like that, let's say a blunt nose. And if it's flying supersonically, generally what we will have is what we call a bow shock wave. Bow shock. This is some kind of oblique shock, and this is a bow shock wave. And we will see now how these are related actually to flight vehicles. So this is what we are mainly interested in, shock waves around flight vehicles. But shock waves also play, and also in the engines of flight vehicles, we will also see that. But shock waves also play an important role. For example, a shock wave is created when an explosion happens, okay? If you remember in 2020, there was a blast that happened in Lebanon in Beirut harbor. I don't know if you remember that from the news. It was a big explosion, and it created a big destruction in the city of Beirut. And that was due to why does the destruction happen? Because these kinds of strong explosions also create a huge shock wave, and this shock wave is a traveling shock wave. And because of the sudden release of extreme amounts of energy, the shock wave is suddenly created. It's like a sphere, and it travels outwards from the explosion location. And it's all treated with the same equations, meaning that, the reason that it basically creates damage is that there is this sudden increase of pressure and temperature occurring across the shock wave when it passes over your apartment, which happened in Beirut, for example. Many apartments were blown away, and many windows were smashed. It's because of the almost instantaneous increase in static pressure and temperature levels. So, of course, this is we are not dealing with this, and this is not our field of. This is another field of expertise. It's not our field, but the physics is the same. Okay, physics is basically the same, and in aerospace engineering, basically flying in a supersonic aircraft means you are basically moving in that shock wave. So we really need to understand its physics, and we need to derive proper equation sets to calculate what will happen after the shock wave. A more straightforward discussion is first we will is related to, let's say, a special case of a normal shock wave, where it's at 90 degrees to the incoming flow. We will first focus on that. And in terms of aerospace applications, we will see many different applications, why these are relevant. And of course, we will see equations in terms of how to calculate flow properties after this. So our first subject, let me use the black color, is the normal shock waves. Normal shock waves. Okay. So let me see these sketches here. So why is this relevant? It's basically we need to understand first normal shock waves quite well, because generally, okay, when the vehicle is flying supersonically, naturally these waves occur, but sometimes we also generate them on purpose, especially when we are designing engines, rocket engines, liquid or solid fuel rocket engines. One application is that in terms of external aerodynamics is the flow around a blunt body. So with a blunt nose, let's say. So this could be even your spacecraft, nose of your spacecraft re-entering from space into Earth's atmosphere. And if you, I don't know if you remember, if you might notice, you know, when, for example, astronauts are coming back to Earth from International Space Station, they get themselves squeezed into a little capsule, and then they re-enter atmosphere, land in somewhere Russia, and then they are picked up. And also during the Mars landing that happened about a month ago, the new Mars rover was inside a similar capsule, and the capsule, it looks something like that. Okay, it does have a blunt surface, and it goes in, of course, into the atmosphere at extremely high Mach numbers. Okay, when this is the case, so if a blunt body is exposed to some supersonic incoming flow, that generates, as I was just describing, what we call a bow shock wave in front of it. Okay, bow shock wave. So basically, this is a quite complex physical phenomena, but what happens is the flow, the streamlines are approaching to the vehicle, and then because of some physical reasons that we will see later and discuss later, the fluid particles traveling at supersonic speeds towards the vehicle, they have absolutely no information that there is a vehicle out there. They do not know until they hit the shock wave. And as soon as they hit the shock wave, they realize that there is actually a body and they have to change direction to go around it. Okay, the fact that they do not have any information of the incoming vehicle towards them, or basically, or if they are moving, they have no information until that there is a body out there until they reach the shock wave, is because of some physical reasons, because of the fact that the disturbances created by the body are basically transported or convected with speed of sound, but the vehicle is moving faster than the speed of sound and all that. So we will discuss this all later, but just bear with me for this instant that these fluid particles, they do not know a body out there. And as soon as they hit this shock wave, they do know it and they have to change direction almost instantaneously. Now, the importance of this bow shock wave is some part of it, especially the front part of it, front section of it, is almost a normal shock wave. So it's at a very high angle, almost 90 degrees to the incoming flow angle. So we need to analyze this, the flow properties, let me use a different color, within this region, just after the shock wave, using normal shock equations that we will see later. So that therefore, for example, if you really want to know what is the pressure acting on the surface, because you designed this vehicle, you don't want it to disintegrate in the middle of the flight, so you need to know the pressure, you need to know the stagnation pressure, you need to know the temperature on the surface and all that, stagnation temperature and static temperatures on the surface. So if you need some heat insulation, for example, if you are re-entering to atmosphere from space, you really need to have a good insulation, otherwise you're going to burn. And that is the fact that the surface gets very high is due to the stagnation temperature of the free stream, basically, which does not change across the shock wave. This stagnation temperature basically is all recovered, all this energy is recovered on the surface, can be thousands of degrees Celsius, so that you have to cool the surface, otherwise the whole capsule will melt. We will see all these equations later. So in terms of these external aerodynamic applications, this is very much relevant. Normal shock waves. Another application is internal aerodynamics. So if we are talking about, for example, a jet engine, and this jet engine could be your regular turbojet or it could be your rocket engine, it doesn't matter. At the very exit of a jet engine, we have a component called a nozzle. So the internal shape of this nozzle generally looks like this. If in a turbo engine, for example, in a rocket engine, it looks more like this. Okay, so this is like the cross section of one of those rocket engines. The thing is, the incoming flow generally is subsonic in these kinds of geometries. If we talk about this rocket engine, for example, at the minimum area location, generally it becomes sonic, and then after this, it becomes supersonic. So the jet exiting from a rocket engine generally is supersonic. The thing is, under nominal design condition, it is like that. But during the startup of the engine and during some operational conditions, while the rocket is accelerating towards space, for example, very changing altitude in a very fast manner, so ambient atmospheric pressure is changing very quickly. In some cases, you could end up with a normal shock wave somewhere here, somewhere inside your nozzle, okay? So that's not something that we want. In design condition, we do not want to have a normal shock wave. But if there is a normal shock wave, first of all, we have to ensure our design operates without a shock wave. But for whatever reason, if there is a shock wave, we need to be able to calculate the flow properties after this shock wave, which is going to decrease the performance of this engine very, very, very significantly. So we don't want that. We will discuss all these also in terms of aerodynamics 2 class, how to handle flow physics in an internal channel flow where we have geometry change like the nozzle shape, and we have these normal shock waves. We will see that. Okay, so these are some basically practical examples. And okay, let me just mention, if you end up with a normal shock wave here, of course, it will be subsonic after a normal shock wave. Your exit velocity will drop down very significantly, which means I think you guys are also taking propulsion class this semester. You may have already seen it, but maybe you will see it. Exit velocity is the most important parameter that determines the thrust generated by a jet propulsion device. So therefore, if there's a sudden reduction in your exit because of the shock wave, there will be a sudden reduction in the thrust level. Not the best situation that you might want to imagine while you are flying. So okay, so these were some applications. Some examples, I must say. There are of course other examples, but some examples of why we need to first learn how to handle a mathematically normal shock waves, what kind of equations that we need to use, plus some of the flow physics that are relevant to normal shock waves. So in order to find what actually happens, or what are the equations that we can use to calculate the parameters, flow parameters that are occurring after the shock wave, of course, our equations are basically known. I mean, the governing equations we have derived so far, mass, momentum, and energy conservation equations are our starting points. So we will make use of those equations to come up with what we call normal shock relations, as is known in the aerodynamics community in the world, to be able to calculate the flow conditions after a shock wave. So basic normal shock relations. This is our topic. Okay. So basically, what we are interested in is that we do have a normal shock wave. sitting in the flow. Okay, and we do have a flow incoming at 90 degrees to that, and our conditions before the shock wave is our list: Mach number, pressure, temperature, density, stagnation pressure, stagnation temperature, and yeah, so the list goes on and on like that. So basically, in order to calculate the flow properties after the shock wave, we have to do basically, or to obtain what we call these normal shock relations, we need to do a simple control volume analysis covering this shock wave. Simple control volume analysis that we teach you guys even in fluid mechanics classes, right? So we select a control volume, something like that. So this is our control volume. We have our first first state, I must say, and then before the shock wave, and the second state after the shock wave. So this is our control volume with its control surfaces and all that. So we assume that the conditions ahead of the shock wave, upstream of the shock wave, are given. So we are interested in calculation of all the other properties after the shock wave. So these equations are related to that. Now, so in order to do this control volume analysis, we have incoming surfaces and outgoing surfaces and all that. In order to consider this, we need to do some, we need to make some assumptions. So I will list them. The first one is that, of course, we consider steady state flow. Consider steady flow. Steady state flow. So meaning that in our governing equations, if there are any partial derivatives with respect to time, they will be equal to 0. And also we know that this is a shock wave. There is no external heat addition to the flow. I mean, the thing is that there is for example, there's a temperature change and everything. The static temperature T2 will not be the same as T1, and we will derive the equation, but we don't obtain that temperature rise by heating up, like burning combustion with some fuel or having a combustion or anything like that. We don't have any of these. But because of the flow is adiabatic, but still the energy of the flow, although the total enthalpy of the flow remains constant, static properties do change. So following our discussion in the beginning of this hour, we know that the flow is adiabatic. So this is our second fact that we know. So therefore, Q dot is actually equal to 0. No heat addition, or I mean, no heat addition or cooling, of course. There is no heat transfer or heat removal, let's say. Okay, so there is no heat addition or heat removal. And what else? The third one is that we assume, we discussed this, but we assume all viscous effects that are present in the flow, all viscous effects are contained inside the shock wave. Okay, inside the shock wave. So all irreversibilities or frictional effects or losses that are created are happening within the thin layer of the shock wave. Outside of the shock wave, at state 1, where we have all these M1, P1, T1, or at state 2, we have all these parameters, the flow is basically inviscid. That's what I'm trying to say, okay? All viscous effects are contained inside the shock wave. And so this is an important issue, and the changes, almost instantaneous changes, are happening, are created, I must say, due to the existence of the shock wave. But outside the shock wave, there are no viscous effects. And since we are dealing with airflow, basically we are neglecting body forces. So no body forces. Okay, this is another important assumption that we must make. Good. So then under these conditions, which are quite actually realistic conditions for a shock wave that is sitting in a supersonic stream, quite realistic. Now we will start working out the equations, working out the continuity equation, mass conservation, that is, working out the momentum conservation and energy conservation, and see how we can actually make use of those equations to come up with some relations to estimate the flow state at 2 after the shock wave. Good. So good. Okay, it's 2:30. So let's give a 10-minute break at this point. Then we will start dealing with the equations, and I will meet you guys again at 2:40. Okay. So let me pause recording, and we will continue in 10 minutes.
Oblique shocks than a normal shock wave?
It depends on the geometry. It depends on the geometry. Kim sormuştu soruyu? Arda yok.
Evet, benim hocam.
Arda. It depends on the geometry. Some geometries could generate, let's say, more like a normal shock wave. Some geometries, geometry meaning your flight vehicle, some geometries could generate more like a series of oblique shock waves. Okay, it totally depends on the geometry. And we will actually see those examples. Okay. So
then
evet.
how can we fly at Mach number, I don't know, greater than 2 or 3? So yes,
Why?
it depends on geometry, but won't flow have always a tendency to go subsonic?
In some places, and depending on the thing is, geometry determines the shock wave structure. There is not going to be a shock wave in reality. There will be multiple shock waves. So the geometry determines the shock wave structure and the number of shock waves, their angles, and depending on that, that determines whether the flow is going to be subsonic or supersonic in different regions around your vehicle.
Okay, hocam. Thank you.
Tamam. It will. I hope it will be more clear as we go along the topics. So we were discussing this control volume analysis. So this is our control volume, and then we start with our continuity equation. So mass conservation, that is. So continuity equation. Let's first talk about this. And of course, first of all, we assume this is a steady state process. So basically, we lose the first term. If you remember, we talked about these terms last week. If it's in that video, you can rewatch it again if you don't remember. So we only have the surfaces. So the mass flow incoming and outgoing from the surfaces, that balance is designated by this integral equation. And when this is written in terms of our selected control volume, basically what we got is this. We have an incoming mass on the left side, ρ1 u1 times area. And area is, okay, maybe instead of scrolling up and down, let me redraw the sketch, make a tiny version of it here. So that's the shock wave. This is the control volume. So area is this area here. Okay, so this is the incoming mass, and it has a minus sign. So this is, let's say, U1, and it has a minus sign this in front of it because of why? Because of what reason? Does anybody know? Incoming mass
Normal
flow.
vector.
Yes, because it's a dot product, right? So dot product is the dot product between the velocity vector and the normal vector of this, which are 180 degrees apart. So we end up with a minus sign. At the exit, we do not have a minus sign. So rho 2 U2 times A must be equal to 0. So from here, rho 1 U1 must be equal to rho 2 U2. Okay. So this is our first relation that we got from as a result of the continuity equation as applied to this selected control volume around a shock wave. The next one is, of course, the momentum equation. Momentum equation. So again, the steady state term is missing. So I'm sorry, unsteady term is missing. So we only have the steady state term, which is the surface integral in the integral equation, which is basically rho v dot ds and v. Now, on the right hand side, we need to have I mean, this shows the incoming and outgoing momentum from that control volume. That must be balanced. I mean, if there is any momentum difference, and the thing is, I mean, the question is there any momentum difference between the incoming and outgoing flow? Meaning, we have streamlines incoming like this with a certain momentum, and we have streamlines exiting from this surface. Basically, from the side surfaces, we do not have much. We do not have anything. So the thing is the exiting momentum different than incoming momentum, or is to put it, to say it more properly, is the outgoing momentum different than incoming momentum? To answer to this question is yes, it is different because of the effect of the shock wave. Outgoing, for example, velocity is different than incoming velocity, first of all. So therefore, there is a momentum balance, momentum change. So this designates that momentum change, and that momentum change must be balanced by forcing on the control volume. And in this case, on the control surfaces, we only have pressure distributions. So pressure-based forcing, so P times ds, of course, along x direction right now, I must say this is x momentum conservation. And by the way, x, I did not write it before, but x, as you might guess already, you might have guessed already, x is aligned with the flow direction. So x momentum conservation equation says that this balance must exist. There are no contributions from the top and bottom boundaries. And so therefore we are only, and there are also no other motion. I mean, streamlines are just flowing from left to right. We have basically straight streamlines. So there is nothing coming in from the side surfaces. Plus, we are not interested in the conservation of momentum. In the case of a normal shock wave, we are not interested in the conservation of momentum in the y direction. Okay, so our main conservation of momentum equation is the streamwise or the x momentum equation. So if we open up this equation now, this conservation of momentum along x, and check out the incoming momentum, balance it with the outgoing momentum. So this is how we do it. For example, rho 1 times minus u1a times u1, and the outgoing momentum from the right-hand side face will be equal to rho 2 u2a times u2. I mean, basically, I mean, we do have a minus sign again because of the dot product, and basically rho 1 u1 times a is the incoming mass flow rate, right? So, I mean, let me rewrite it in parentheses. This is minus rho 1 u1a times u1, and I know that this is equal to m dot 1. Okay, so so mass times velocity is momentum, and in fluid mechanics, mass flow rate times velocity is momentum flow rate, momentum flux. Anyway, so that is the balance between outgoing and incoming momentum. That must be equal to pressure forcing. So on the right-hand side of the equation, we have a minus P1 times A plus P2 times A. So if I rearrange these terms, it gets a simplified. It gets in a slightly simplified form: P1 plus rho1 U1 square must be equal to P2 plus rho2 U2 square. So this is now our second equation. In addition to this, here, this was our first equation. And now we have our second equation that we obtained through conservation of momentum in that control volume around the shock wave. Is this it? No, because we have more. This is only two equations, but we have more unknowns. So we also take into account the third conservation equation, which is the energy. So conservation of energy equation. Now, as applied to this control volume, that is situated basically around this shock wave. Again, steady state process. So on the basically steady state process, again, meaning that we need to consider outgoing energy right now, compare it to the incoming energy, and the balance should be related to whatever is changing the energy in as a summary. So incoming, I mean, the total energy is basically internal energy plus kinetic energy. In this case, we ignore body forces, so there is no potential energy, and energy flux. That is this whole thing integral is representing the energy flux balance from the left compared when we compare the right hand face to the left hand face, for example, of the control volume. Now on the right hand side, what changes this energy level? This energy level, first of all, we do not have any heat transfer, so it's adiabatic basically. We do not have any external work that is given. There's no propeller, there's no turbine, there's nothing that is doing work on the fluid, but there is what we call flow work. So that's basically in the equations pressure times V dot ds. So and there's no other energy source other than this. So if we apply it to the control volume, now we do have the incoming energy flux, E1, internal energy, U1 square over 2 kinetic energy times U1 times area, plus outgoing energy flux, rho2, E2 plus U2 square over 2, U2A. So incoming versus outgoing energy balance. This is the left-hand side of the equation. And on the right-hand side, we have pressure of flow work related terms. So P1 U1 times A and plus P2 U2 times A. So now this is basically our third equation, but before that, just need to rearrange it a little bit because it looks a little bit, it looks better if I do that. Collecting, let's say, all the one subscript terms to the left-hand side, I have P1 U1 plus rho1 times E1 U1 square over 2 times U1 must be equal to the same thing with subscript 2. So rho2 E2 U2 square over 2 times U2. It can even I can make it a little bit. I can make it look even a little bit better. How? By invoking continuity equation. So let's do that. So dividing this equation by ρ1 u1, which is also equal to ρ2 u2 from continuity equation. Then what we could obtain is that, so we are basically merging two equations now, continuity and energy. When I combine them, I end up with this equation, P1 over ρ1 plus E1 plus U1 square over 2 is equal to P2 over ρ2 plus E2 plus U2 square over 2. So that, whatever this quantity is, it must be conserved after the shock wave, as you can see. Okay. And what else? We can remember, of course, these two terms. Let's use red color. These two terms, this is P over rho plus E in general is the definition of enthalpy. So basically this is H1. And therefore we have also H2, static enthalpy, that is. So therefore H1 plus U1 square over 2 must be equal to H2 plus U2 square over 2. And we do know that H1 for a calorically perfect gas is equal to Cp times T1, and H2 is equal to Cp times T2. You can see where this is going. Now, this also implies a relation between static temperature change across the shock wave as well. So just to summarize what we got for the shock wave relations, I mean, we will further manipulate them, because right now, the thing is we have all these equations, but I don't see a Mach number, for example. Where is the Mach number, right? We just see velocity, temperature, pressure, density, that's fine. But I don't see a Mach number. We have to make sure we see that in these equations. We will come to that later. But just to summarize, we have three now major equations that relate the before the shock properties to after the shock properties. So ρ1 u1 is equal to ρ2 u2 comes from continuity. From momentum, we have the other equation. So P1 plus ρ1 u1 square becomes equal to P2 plus ρ2 u2 square. And from the energy, basically H1 plus U1 square over 2 must be equal to H2 plus U2 square over 2. So, and also using, so let's see how many unknowns that we have here. We have what we are trying to calculate is, for example, ρ2, we do not know ρ2, P2 is not known, H2 or let's say T2 is not known, and also U2 is not known. We basically have 4 unknowns. But right now we have only 3 equations. Of course, we need one more equation to close the system. And the 4th equation is basically equation of state. So, I mean, in addition to the fact that H is related to temperature, I've already written that, so I'm not considering that. But the 4th equation is basically P2 is equal to ρ2 R T2. So this is equation of state as the 4th equation. And so plus 1 makes it 4 equations and 4 unknowns. So now the shock wave problem is represented by a closed system of equations, 4 equations and 4 unknowns. So it's we can represent the physics of the shock wave with these 4 equations, which can be solved to obtain these 4 unknowns. Of course, given all the conditions, all the parameters at state 1. So those, of course, obviously must be given. Okay, good. Let me see. So now we will divert a little bit, because at this stage we have all of our equations and everything. I mean, I can obtain these parameters. I can obtain them. That's not a problem. We have a closed set of system of equations. But the problem is I do not see Mach number here. Okay, what will be the Mach number? And of course, you might remember, I don't know, from your previous classes and everything, Mach number is related, in fact, I mean, we know its definition. Its definition is the speed, the flow speed after the shock wave as a percentage of the speed of sound after the shock wave. Okay, the question is then, what is speed of sound after the shock wave? Again, from your previous classes, you might remember that speed of sound in general is actually a function of temperature. Okay, if we are talking about A2, so it will be a function of T2, and in reality, this is, we know that you might have seen that, we will actually discuss this now, but you might have seen before that this is actually, the function looks something like this: gamma specific heat ratio times gas constant times temperature. This is the equation. So the thing is, so now, first of all, since this is a compressible aerodynamics class, we need to understand a little bit flow physics related to the speed of sound. And then we will come back to these equations, do necessary modifications, and then we will actually start to see the Mach number 1 and Mach number 2, M1 and M2 actually in the equations. Because normally this is our ultimate purpose, given a set of, and we will see in reality that all the properties that we are interested in, pressure changes, temperature changes, velocity changes, even entropy changes, every property that you might imagine is actually a function of the Mach number change. So we will, therefore, knowing the Mach number is very important. Writing the equations in terms of Mach numbers, M1 and M2, are very important. But before we go there, now we will discuss a more fundamental subject of speed of sound, this A that we are interested in. So we need to understand this one a little bit better, speed of sound in general. Okay. So the thing is, as the name suggests, it's basically, when you create some kind of disturbance in air, and at this very moment, I am creating a disturbance in air, although I'm just sitting in my chair and doing nothing. And that disturbance is because the fact that I am talking. Okay. In my throat, in the sound system in my throat, I make use of it to generate basically small pressure disturbances in air. Those disturbances basically travel with speed of sound. And then, of course, those disturbances are picked up with this electronic transducer, which I'm using. It's a microphone, converts those pressure fluctuations in air to voltage fluctuations. And then instead of now that information, once it's turned into voltage fluctuations, now it travels with speed of light. So you can almost hear me instantaneously. But if we were in the same room for face-to-face classes, sound travels when I'm talking, and it does travel with a finite velocity. Okay, so first of all, we need to be aware of this. And not only that, so sound travels with finite velocity in a medium, I must say. In our case, our medium is air, so we are very much interested in how fast does the sound travel in air, but in general, sound travels with different velocities in different mediums, like in a solid medium or in a liquid medium, it travels with totally different velocities. For example, I think we discussed this before, speed of sound in water is much, much higher than the speed of sound in air. Speed of sound in solids are much higher than the speed of sound in air or water. So the thing is, this physical mechanism of sound propagation. So the thing is, sound is like a disturbance that is created. That propagation of that disturbance basically occurs in a molecule, or how fast it occurs is basically based on the molecular motion that we have. And it travels with, when we say sound traveling, basically what is actually traveling are very weak pressure waves that we create in air. And it's like if you take a small piece of stone, drop it in water, it creates continuously propagating waves, right? That's exactly what happens when you create a disturbance in air, whether by waving your hand or whether by talking. That information, information that you disturb the air, propagates by small pressure waves, like those waves in water, like with small pressure waves in a spherical manner all across the source that that the disturbance was created by. So initially what happens is you disturb that your motion, your hand motion, for example, you're waving your hand, disturbs some molecules, some air molecules, and those air molecules go and hit other air molecules, and this disturbance keeps going out and continuously propagated to like a domino effect. Okay, so therefore, of course, in the macroscopic sense, not in the molecular sense, but in the macroscopic sense, we let's say understand this molecular motion as waves. We see waves of small pressure disturbances propagating out. So if you have, let's say, a small point and you have created a pressure disturbance, that this disturbance will create waves. These waves will propagate out and their propagation speed will be the speed of sound, A, and these waves will be like the waves on the surface of water when you drop basically a small piece of rock. Their magnitude, the pressure change, so let's say you are sitting here, okay, watching this, and that some of these waves comes and hits you and passes over you, that creates a minor pressure jump when it's passing over you. So it's a very small amplitude pressure change, and your ears can pick up that, okay? Your ears can pick up that pressure change, and your brain interprets that pressure change, and you understand what this person is talking about. So basically, this wave propagation happens in any medium with speed of sound in that medium. So this, okay, let's say sound wave propagation, because wave propagation is general. We are not talking about electromagnetic wave propagation. We are talking about sound wave propagation. So this happens with speed of sound anywhere. So any disturbance that you create in air will be propagated with speed of sound. Now, now let's see what else. Generally, the average velocity of speed of sound, I mean, this how fast is speed of sound? It's about 320 meters per second in air, or in water it's more than 1000 meters per second and things like that. But how do we calculate it? And we do know it's probably a function of temperature, but in reality it's based on, I mean, how fast these pressure waves propagate is based on molecular activity. So generally, kinetic theory of gases is used to estimate that the value of speed of sound in a given medium, in a gas medium, let's say. In air, we know that, but for example, for carbon dioxide, let's say you have a room filled with carbon dioxide, then speed of sound could be different, okay? So it depends on the kinetic theory of gases, and it can be calculated from the molecular level. I'm not going to go into those details, but the thing is, since this molecular motion, since this is happening, this propagation is happening basically due to molecules that are moving, and the global parameter of temperature is basically an average or macro scale indicator, average indicator of molecular velocity, So we should, I mean, we generally expect that the propagation wave speed must be related to temperature, because temperature is a direct indicator of that molecular velocity levels. So it must be a function of temperature, and that function in reality can be derived from, as I said, from the kinetic theory of gases. So we will continue our discussion based on two cases. We will consider a moving sound wave. So let's say consider a sound wave that is propagating, propagating through a gas. Of course, we are limiting ourselves to, our medium is air, so a gas in general, through a gas with velocity a. So it's moving, the propagation speed is speed of sound, so with velocity a.
Hocam,
Evet.
may I ask a question? It might be irrelevant to this topic, but I'm wondering some information about the speed of sound. Also, can I ask it in Turkish, because I don't know how can I tell it in English?
Okay, let's do it quickly.
Hocam, şimdi biz dünyada yaşadığımız için belli bir atmosferin içindeyiz ve sürekli havayı disturb etmemiz gerekiyor.
Evet.
Bu da sürekli havanın içindeki molekülleri titreştireceği için biz sesle bir şeyler yapmış oluyoruz.
Evet.
Biz hızları neden o zaman sese bağlı değil de belli bir kilometre saat gibi birimlerin üzerinden tanımlıyoruz? Çünkü
İşte-
ses hızı sürekli değişmeyecek mi?
İşte onun için
Density, hız.
havacılıkta kilometre bölü saat cinsinden yapmıyoruz çünkü. Neden yapıyoruz? Mach sayısı konuşuyoruz. Her şey ses hızına bağlı.
Peki hocam, hani uçağın şeyini bulurken bir velocity şeyimiz var ya, tanımımız var ya.
Hı hı.
Oradaki kilometre bölü saat nereden geliyor peki?
Evet, ama o bizim için irrelevant. Bizim için önemli olan Mach sayısı. Uçak mühendisleri için.
Anladım.
Yani kahvede konuşurken kilometre bölü saat konuşabilirsin, ya da annene babana anlatırken veya ne bileyim arkadaşlarına havacılık, hani mühendisliği okumayan arkadaşlar anlatırken kilometre bölü saat anlatabilirsin. Çünkü günlük kullanımda insanlar tabii daha alışık kilometre bölü saate, ama bizim için o önemli değil. Bizim için Mach sayısı önemli.
Teşekkür ederim hocam.
So let's come back to this. So we, in the first, the thing is, we imagine now a propagating sound wave. So this wiggly line here, let's say it's the sound wave. Somehow a disturbance is created. I don't care what created it, but something created a traveling sound wave or propagating sound wave, and it is moving with velocity a from right to left. and initially through a gas, and initially before the sound wave actually hits the gas is not moving. So on the left, we have what we call stagnant gas. So it's basically sitting there. It's not moving at all. The gas could have a certain initial pressure. It could have certain density and temperature. And when this wave passes over this gas, okay, and basically after the wave has passed over this gas, there will be slight infinitesimal changes to gas, the properties of the gas, and the state of the gas will be now slightly different. After this wave has passed over it, P will be slightly different, because I told you these waves are quite weak waves. So the disturbances they create when they pass over you, for example, are small, but there is a disturbance. So there will be a slight change in temperature, and there will be a slight change in density. Okay, slight change in density. So this is a sound wave propagating with a velocity a into a stagnant gas. Now we could imagine similar physical process happening in a slightly different manner. Instead of imagining a stagnant gas and the sound wave passing over the stagnant gas, we can, let's say, go to another frame of reference, meaning that we can fix ourselves on the propagating sound wave itself. Let's say you took a chair and started sitting on the sound wave, you're traveling with it. In that case, what you would see is the gas actually will be moving towards you with speed of sound, right? So let's say we have the same wave, but now it's fixed, it's not moving. So let's say this is now fixed sound wave, it is not moving, but in that case, what you would see is the gas oncoming towards you with speed of sound. The gas would still have its initial properties, and when the gas now passes, it's flowing through, it's coming towards you, towards this standing sound wave with the speed of sound. Basically, you would experience a change again after it passes the sound wave, a change in pressure, a change in temperature, a change in density, and now, since the temperature will be different after this sound wave, you would also express a change in speed of sound at the gas state after the sound wave. By the way, this kind of sketch is basically analogous to this. So these two are analogous. So they represent, analogous means they represent the same physical process. Physical process does not change when you do these two representations. Now the thing is, this sketch that I made on the right-hand side, where we have a stationary or not moving sound wave in a moving gas, looks very much like a shock wave, right? Only thing is that this is not a shock wave. This is a sound wave. A shock wave is you can imagine, maybe you can think about it. You think about a shock wave is an extremely strong sound wave, maybe. A sound wave is a wave. It just creates infinitesimal change in the flow properties as the gas is moving along. So, because of the fact that it only creates very small changes in the fluid properties, it makes a big difference than a shock wave. We will see what that difference is. So let's focus on this case for a second. So let's focus on this case and see what we got. Now, first of all, flow is one-dimensional, so only from left to right. The gas is moving in a kind of a one-dimensional sense. So one-dimensional meaning only X components of momentum, for example, will be relevant. And similar to the shockwave problem, this is adiabatic. The sound wave does not create any heat addition or anything like that, so it is also adiabatic. And the changes are very small. So these delta changes or different infinitesimal changes, dp, dt, d rho, dA, are infinitesimally small. So gradients across the sound wave are, let's say, infinitesimally small. And this is quite realistic, because if you try to measure, let's say, I don't know how you can do that, but if you can try to, and microphones do that, you need to really have, for example, very precise measurement devices like microphones. You can measure slight pressure variations in a room, for example, and they are very small. So that mathematically we can call them infinitesimally small. And therefore, since changes are very small, unlike a shock wave, so maybe I should put unlike a shock wave where gradients are very strong and changes are very, very big. So in this case, basically, what is the result of this? What is the result of the fact that the changes are very small? The influence of dissipative phenomena becomes almost negligible. Influence of dissipative phenomena or what we can say irreversibilities, influence of irreversibilities that are created by this very weak sound wave, irreversibilities are almost negligible or is negligible. Well, in this case, now we have an interesting phenomenon. Now we are talking about a wave similar, which looks like it is similar to a shock wave, but it is very weak, creates only infinitesimal changes in the flow field, and it is adiabatic like a shock wave, but there is a big difference. This wave is basically reversible because the dissipative effects occurring within a sound wave is almost non-existent, almost negligible. In that case, now we are dealing with a different physical process. It was adiabatic already, and now it is reversible. So basically, a sound wave is both adiabatic and reversible, so meaning that it is an isentropic process. It's an isentropic process. Was a shock wave an isentropic process? No, because there's huge gradients and huge changes in all flow properties, and the irreversibilities or dissipative phenomena is not negligible at all in a shock wave. Anyway, so sound wave is an isentropic process. So the question is, well, what if we actually apply our conservation equations like we did, like we applied them to a normal shock wave? What if we now apply them to this situation? We take a control volume around the sound wave, apply mass, momentum, and energy conservations, and let's see what we get. Okay. And keeping in mind that now this is an isentropic process. So let me write the continuity equation, then the rest I will continue tomorrow afternoon. For the continuity equation, basically it will be equal to rho times velocity, which is A on the left-hand side, will be equal to the density after the sound wave, rho plus d rho, multiplied by speed of sound after the sound wave has passed. So if I just open up this is equal to rho a plus rho dA plus a d rho plus d rho times dA. Now here I'm multiplying two very small numbers, so these are negligible, negligible basically. Okay, so here what did I get? I get rho A is equal to rho A plus rho dA plus a d rho. So these cancel obviously, so I get 0 is equal to rho dA plus a d rho. So I will keep this equation aside. So I will call this equation 1. We will. This is the result of the continuity equation as applied to this control volume around one single standing or stationary, not moving sound wave. And same approach like we did, did for the normal shock wave equation. And next thing what we're going to do is write the momentum equation only along x direction, so conservation of momentum, and we will continue from this point tomorrow because it takes a little while to do that, to do this derivation. Great, so let me stop here for today, and I will meet you guys tomorrow at 1:40 again. Any questions?
John, I have a question actually.
Yes, please go ahead.
John, in the shock waves, actually, the third assumption we said viscous forces are in the shock wave. So, is there any relation between the reversibility and irreversibility of the normal wave and shock wave?
There's no such. I think you are confused a little bit. I didn't say. I mean, normal shock. There's normal shock wave and there's sound wave.
Yeah, sound wave. Yes.
So
Sound.
the big difference is that the frictional effects or viscous losses that are occurring within a sound wave is almost negligible, because it just creates a very, very tiny disturbance in the air, in the gas. A shock wave is not like that. It creates a huge disturbance in the gas when the gas passes over it.
John, then why don't we consider that effect in the equations?
Which effect?
Viscous effects.
Because of the fact that I just told you, in a sound wave, these effects are negligible. So the viscous effects, frictional effects are negligible. Why? Because the changes are infinitesimal. There's very tiny, tiny amount of change happening to pressure, for example. Okay, these changes are very small. So gradients are very small happening in a sound wave. Not the case for a normal shock wave.
Thank you.
Any other questions?
Hocam, when the recitation will start approximately?
Sorry, what?
When the recitations will start approximately?
I'm not sure. I will check with the course assistants. Okay, I'm not sure right now, but it should start soon, because we are just starting the basic main subject matter, so it will start soon, I guess.
Okay, thanks.
Any other questions? Okay, well, so let's meet again tomorrow, okay? Tomorrow afternoon. So let's stop recording and